The enemy calls it impossible. Let's show them what American steel can do. It was the 20th of August, 1942, at Henderson Field, Guadalcanal. A Marine Corps engineer battalion, mud-caked and grim, worked relentlessly under the intermittent thunder of Japanese artillery, connecting interlocking steel panels across what had been a muddy coral strip. Just 2 weeks earlier, this ground had been an unfinished Japanese airstrip. Now, American fighters were poised to land, preparing to take the fight directly to the enemy. Japanese commanders watching from the contested hills were gripped by utter confusion. Building an airfield, a functioning base capable of handling heavy aircraft, demanded months of toil, massive concrete pours, specialized heavy equipment, and dedicated engineering battalions working day and night. The Marines had achieved this miracle in a mere 13 days. What those Japanese observers witnessed was a profound revolution in military logistics, a disruptive technology that Axis planners had failed to foresee. It was a solution so simple it bordered on the absurd. Steel mats, perforated panels of metal, delivered on the back of trucks, and unrolled across the earth like industrial carpets. The Germans, when they finally learned of it, dismissed it as impossible bravado. The Japanese possessed no comparable technology whatsoever. By the close of the war, American aircraft were operating from locations that, by conventional metrics, should have required months to prepare. From tiny, wind-swept coral atolls that could barely support a scrub bush, from muddy fields that became instant quagmires after the slightest rain, and from unstable volcanic ash that traditional construction methods could not stabilize. This is the story of how American industrial genius created a weapon that never fired a shot, yet proved decisive in winning the war in both major theaters, a logistical game-changer that arguably shortened the Pacific campaign by months, and granted Allied forces an operational flexibility that their Axis counterparts could not, would not, match. The weapon was pierced steel planking, PSP, and it fundamentally changed everything. In 1940, American military strategists faced a logistical problem that seemed utterly insurmountable. Modern mobile warfare demanded air superiority. Air superiority demanded airfields, and airfields demanded many, slow months of construction time. The German Blitzkrieg had brutally demonstrated the necessity of tactical air support. However, German forces operated primarily in the highly developed European theater, where they could readily capture and utilize hundreds of prepared airfields in France, dozens in Poland, and established bases across the Western Soviet Union. American planners, however, gazed across the vastness of the Pacific and saw an entirely different enemy. Thousands of islands, most devoid of any infrastructure, many lacking fresh water, some barely above sea level, and all separated by crushing distances of open ocean. Traditional airfield construction followed a mercilessly slow process. Survey the terrain, clear the vegetation, grade the land, establish deep drainage, compact the soil meticulously, pour concrete or lay asphalt, wait for the mandated curing time, and finally install navigation aids. The calculated timeline, 4 to 6 months for a single operational airstrip. The U.S. Army Corps of Engineers warned that island hopping across the Pacific at that agonizing pace would stretch the war for years, possibly decades. Military planners grasped the dilemma clearly. The enemy would have either evacuated or impossibly reinforced every position before the Americans could make their crucial airstrips operational. They needed a solution that was portable, capable of rapid deployment, and functional on terrain that any conventional engineer would immediately deem utterly unsuitable. Axis intelligence, monitoring American communications regarding these crippling logistical challenges, drew a seemingly logical conclusion. The Americans would be forced to capture existing Japanese airfields. This meant the U.S. forces would have to fight a grinding, costly battle for every single installation. Japanese defenders could prepare extensive fortifications, turning each island into an impregnable fortress. The strategic implication for the Axis was crystal clear. Fortify every airfield, make them unbelievably expensive to capture, and thereby slow the American advance to a crawl. Both Axis powers operated under the fatal, shared assumption that airfields were strategic choke points. Whoever controlled the airfields controlled the theater. What neither side anticipated was that the Americans would simply, brilliantly, ignore their airfields altogether. The solution to this global logistical crisis emerged from a highly unlikely source: the Carnegie, Illinois Steel Corporation. Engineers there had been experimenting with perforated steel decking for purely industrial purposes. The process of perforation significantly reduced weight while remarkably maintaining structural integrity. A solid steel plate strong enough to support the heavy loads of a bomber would be too heavy and slow to transport efficiently. A perforated plate, however, could achieve similar load-bearing capacity at a fraction of the weight. An Army engineer named Major Gerald G. Groich, the chief engineer at Carnegie, Illinois Steel and the holder of over 100 patents, immediately recognized the staggering military potential. He proposed a system of interlocking steel planks, each 10 feet long and 15 inches wide, with precise, specific patterns of holes punched through. These holes served two critical functions. They reduced the panel's weight and allowed for effective water drainage. Most critically, the planks featured robust hooks along their edges that would lock adjacent panels tightly together. The concept appeared simple, almost too simple to be revolutionary. Military skeptics voiced immediate and sharp objections. Bare steel would sink into soft ground. The perforations would create structural weak points under massive weight. The interlocking mechanism would fail under the twisting stress of landing aircraft. The landing gear would undoubtedly catch in the holes, and sharp coral and volcanic rock would rip the panels to shreds. The Army Corps of Engineers launched rigorous testing at Langley Field, Virginia, starting in December 1939. Test 1. Load bearing. Engineers laid 200 panels over completely unprepared soil and drove a fully loaded B-17 bomber weighing 65,500 pounds across the surface. Result: the planking supported the aircraft's weight without any visible deformation. Test 2. Weather resistance. Panels were subjected to simulated tropical conditions: blazing heat, high humidity, corrosive salt spray, and extreme temperature fluctuations. Result: minimal corrosion after 6 months of punishing exposure. Test 3. Rapid deployment. Engineers challenged a standard construction battalion to lay a 5,000-foot runway using the steel matting during field exercises in November 1941 at men pronounced Mean, North Carolina, using only basic hand tools. Time to completion: 11 days for the very first installation. One construction battalion, a fully operational airstrip capable of handling heavy bombers, accomplished in 11 days on their first attempt. The town where this vital practical deployment occurred gave the technology its enduring name: Marston Mat, a contraction of men and matting, named not after a person, but after men, North Carolina. The implications were immediately and blindingly obvious to American planners. With experience, construction times would plummet dramatically. The first combat deployment came sooner than anyone expected: Bluey West, one airfield in Greenland. Construction began in the brutal Arctic conditions of fall 1941, and the first aircraft landed on January 24, 1942. Greenland proved the concept worked in extreme cold, but the Pacific would unleash its true strategic value. Meanwhile, American production ramped up to colossal levels. By January 1943, steel mills were producing pierced steel, planking at a rate approaching 1 million square feet per month. The mats were standardized panels, packaged for efficient ocean transport and ready for immediate deployment. Each panel weighed a manageable 66 pounds, light enough for 2 men to carry, yet strong enough to support a P-51 Mustang. A standard C-47 transport aircraft could carry approximately 74 panels, enough to create over 1,100 square feet of runway surface. Land the aircraft, unload the panels, have an engineering team lay them out, and take off again, all within 6 hours. The real revelation was the scale of the deployment. A single Liberty ship could carry enough matting to construct a complete 5,000-foot runway, including parallel taxiways and dispersal areas, totaling approximately 2 million pounds of steel. This entire material load required less than one-third of the ship's cargo capacity. This meant that every transport convoy could carry not just troops and supplies, but entire airfields, deployable on arrival and operational within days. The defining Pacific test came in August 1942 at Guadalcanal. Henderson Field, an incomplete Japanese construction project, was little more than a primitive coral strip that instantly devolved into a muddy morass during the frequent tropical downpours. Aircraft bogged down, takeoffs became perilous, and air operations would have ceased entirely during heavy rain without intervention. The 1st Marine Engineer Battalion, working alongside the 6th Naval Construction Battalion, had steel matting available from the initial landing supplies. They began laying the panels directly over the existing coral surface. No additional grading, no foundation preparation, just interlocking steel panels connected by simple edge hooks. Marine engineers, working in teams of 4, operated under the constant threat of artillery fire. 2 men would position the panel. 2 would lock it to the adjacent panels, using hand hooks. They maintained a pace of approximately 500 panels per hour when not diving for cover from Japanese shelling. The runway was operational in 13 days. More critically, it remained fully operational during the next torrential rainstorm. Water drained through the perforations, the steel surface provided consistent traction, and aircraft could operate regardless of the weather. Japanese commanders monitoring Henderson Field were immediately struck by the change. American air operations continued relentlessly. Rain or shine, what had been a vulnerable logistical choke point became a reliable, permanent base of operations. The strategic implications were profound. Traditional airfield construction created predictable patterns. Intelligence could identify construction activity, survey teams, heavy equipment, extensive ground preparation from aerial reconnaissance days or weeks before an airfield became operational. Defenders could anticipate where American aircraft would operate and position forces accordingly. Marston Mat obliterated this equation. Aerial reconnaissance might show trucks and some organized activity, but no obvious signs of conventional airfield construction. No concrete mixers, no giant grading equipment, no months-long timeline that brazenly telegraphed American intentions. The intelligence advantage shifted dramatically. American forces could now select landing zones based on sheer tactical requirements, rather than being constrained by existing infrastructure. They could establish air support within days of securing a beachhead. If an airfield came under intense pressure, they could abandon it and rebuild an entirely new one elsewhere, with the same reusable materials. The Pacific Island hopping campaign demonstrated this flexibility in operation after operation. Tarawa, November 1943. Marines secured the island after 76 hours of horrific combat. Aviation engineers landed with the early waves, bringing steel matting and landing craft. Before the island was even fully secured, they began laying runway panels over the damaged Japanese airstrip. American fighters were operating from Tarawa within 96 hours of the first Marines hitting the beach. Japanese planners had fatally assumed that Tarawa's capture would deny Americans an operational airfield for weeks. The deliberately damaged runway would, they calculated, require extensive reconstruction. Kwajalein, February 1944. The atoll consisted mostly of soft coral, a material that could never support conventional runway construction. American engineers laid 6,000 feet of matting directly onto the soft coral surface. Heavy bombers were operating from Kwajalein within a single week of its capture. Saipan, June 1944. Japanese defenders had thoroughly destroyed existing airfield infrastructure during their retreat. American engineers simply covered the damage with steel matting. The airfield was operational before the island was even fully secured. The pattern repeated across the Pacific. Every island the Americans took became an airbase, not eventually, but immediately. Japanese defensive doctrine, built on the assumption that American advances would be hopelessly constrained by logistics, proved fatally incorrect. The technology was not confined to the Pacific. In North Africa, engineers used steel matting to create airfields in shifting desert sand. Sand that conventional runways would have taken months to stabilize. British and American forces could establish tactical airfields within days, providing crucial air cover for highly mobile armored operations. In Italy, matting covered muddy fields that instantly turned to impassable soup during the winter rains. Allied bombers maintained operations against German positions, regardless of the weather. Luftwaffe planners, counting on winter conditions to effectively ground the Allied air fleet, had their advantage completely eliminated by the steel mats. After D-Day, engineering battalions landing on the Normandy beaches had steel matting among their initial equipment manifests. Within 72 hours, fighters were operating from French soil, not from captured airfields, but from fields that had been peaceful pastures the previous week. German defenders watching Allied operations from a distance struggled to comprehend what they were seeing. Fighter aircraft taking off from locations that showed no signs of conventional airfield construction. The reconnaissance photos showed trucks and human activity. But the essential infrastructure, the concrete and grading, was simply absent. The staggering production numbers tell the ultimate story of American industrial capacity. Between 1942 and 1945, U.S. manufacturers produced approximately 2 million tons of pierced steel planking, enough to construct roughly 954 miles of runway, an area equivalent to several dozen major airfields. This 2 million tons of steel represented a significant portion of American steel production, dedicated to a single, crucial logistical innovation. The cost per panel was approximately 3.31 inches, 1,943. The cost of a full, conventional concrete airfield ranged from 2 to 5 million. A complete Marston Mat airfield, however, cost roughly 200,000 inches, materials alone, 1/10 the cost. Operational in 1/30th the time. Historical records confirm that neither Germany nor Japan developed any comparable technology during the war. Air and Space Forces magazine concluded that both Axis powers had nothing remotely similar to American pierced steel planking. German logistics were rail-based. The matting worked best with the truck-based logistics that could deliver materials directly to remote sites, a motor transport capacity German forces simply lacked. More critically, by the time the technology's importance became clear, Germany was fighting defensively, making rapid airfield construction a less relevant priority. Japan's industrial capacity, already stretched thin maintaining its navy and air forces, could not support large-scale matting production. And by mid-1944, American forces controlled the sea lanes necessary to transport materials between islands anyway. The Axis response to the American steel matting defaulted to trying to destroy it after it was already in place. Japanese artillery and Luftwaffe bombers targeted the matted runways, only to discover that the steel matting was surprisingly difficult to disable permanently. Conventional runways, when bombed, required massive repair. Craters had to be filled, concrete poured, and lengthy curing time enforced, shutting down a concrete runway for days or weeks. Matted runways were different. A bomb strike might destroy a few panels. Engineers would simply disconnect the damaged sections and install replacements. Typical repair time. American engineering manuals noted that a 500-pound bomb direct hit typically damaged an area requiring the removal and installation of approximately 40 panels. A 4-man crew could complete this operation in less than 3 hours, returning the runway to full operational status immediately. The operational flexibility extended far beyond simple construction speed. Matted airfields could be expanded or reconfigured with minimal effort. Need a longer runway. Add more panels. Need more parking. Lay panels adjacent to the main strip. Need to relocate the entire airfield. Disconnect the panels, load them onto trucks, and rebuild elsewhere. American forces exploited this repeatedly. In the Philippines, Engineers relocated entire airfield complexes 3 times during the campaign, moving with the advancing infantry to ensure continuous close air support. In New Guinea, matted runways were progressively extended from 3,000 feet to 5,000 feet, and eventually to 7,000 feet. For B-24 operations, all without shutting down ongoing flight operations. The environmental versatility proved equally invaluable. Steel matting functioned on surfaces that defied conventional construction. On soft coral atolls, the panels distributed weight sufficiently to prevent sinking. In areas of volcanic ash, the matting created a structural layer that spanned the unstable substrate. In permafrost regions, the flexible panels accommodated freeze-thaw ground movement without structural failure. In jungle environments, the matting provided drainage through its perforations, while maintaining a solid surface against tropical downpours. In desert sand, the perforated design allowed wind to pass through, reducing drift accumulation. Each environment presented unique, paralyzing challenges for traditional construction. Marston Mat worked in all of them. The human element of this story is found in the experiences of the engineering battalions who installed the matting under combat conditions, operating at the deadly intersection of logistics and warfare. Engineers described working in shifts, maintaining 24-hour installation schedules, with panels pre-staged in stacks near the work sites to minimize transport time under fire. Installation crews wore full combat gear, ready to take cover. Some units reported laying matting while under direct small arms fire, using bulldozers as mobile shields. Casualties among the engineering units were significant, with units like the 1,892nd Engineer Aviation Battalion, an all-African-American unit, suffering heavy losses primarily from artillery fire while constructing airfields during the Okinawa campaign. Yet the matting was laid, the airfields became operational, and tactical air support arrived days or weeks ahead of schedule. The psychological impact on enemy forces was profound. Japanese defenders on isolated garrisons understood that American air superiority meant inevitable defeat, but they had not anticipated how swiftly that air superiority would arrive. Islands they expected to defend for months came under sustained air attack within a week of American landings. Captured Japanese officers consistently expressed shock at the speed of American airfield construction, having calculated defensive strategies based on conventional engineering timelines. When reality contradicted those calculations by an order of magnitude, it fatally undermined confidence in all their strategic assessments. The matting's success generated profound secondary effects, compelling American tactical doctrine to evolve to exploit this rapid airfield construction capability. Operations previously deemed logistically impossible became standard practice. Marine Corps amphibious doctrine was swiftly rewritten to assume close air support would be available within 48 to 72 hours of a landing, rather than weeks. This fundamentally changed assault planning. Marines could land with lighter artillery, knowing air support would arrive quickly to provide heavy fire support, allowing for faster landing schedules and reducing the logistical burden on initial waves. Army Air Force targeting doctrines adapted to the new reality that forward airfields could be established almost anywhere, enabling fighter groups to respond to ground force needs in days, not months. Strategic bombing campaigns benefited similarly. As Allied forces advanced across Europe and the Pacific, bomber ranges to target areas drastically decreased because forward airfields appeared so rapidly. For 17 seconds, operating from hastily constructed matted airfields in France or Belgium cut mission distances by half, reducing fuel requirements, increasing bomb loads, and decreasing crew fatigue. The economic implications extended beyond simple cost savings. Traditional airfield construction required specialized cement, asphalt, and heavy construction machinery resources that were globally scarce during wartime. Steel matting used common materials that could be mass-produced by facilities across the United States, meaning the program wasn't bottlenecked by specialized suppliers. Labor requirements dropped dramatically. A conventional airfield might require 500 skilled construction workers laboring for 6 months. A matted airfield required 100 combat engineers working for 3 days once experienced. Those 500 skilled workers could be deployed on other crucial projects. Transport efficiency created further advantages. Concrete and asphalt required specialized transport ships with specific storage conditions. Steel matting could be loaded onto any cargo vessel. It was even transported on returning Liberty ships, utilizing otherwise empty cargo space after delivering troops and supplies. This efficiency meant the logistical tail for airfield construction effectively disappeared. By 1945, the technology had become so routine that American forces simply took it for granted. Matted airfields appeared wherever operations required them. The extraordinary had become the ordinary. After the war, Marston Mat found new life. The Berlin airlift in 1948 initially relied on matted runways at Tempelhof Airport. Korea saw extensive use of steel matting, with nearly 30 million square feet deployed on airfields. Vietnam featured hundreds of thousands of tons laid throughout South Vietnam, with improved variants developed. The technology that helped win World War II continued serving American forces for decades. Modern military engineering still utilizes descendants of the original Marston Mat design. Materials have evolved. Aluminum replaced steel. Composites offer better performance, but the fundamental concept remains unchanged. Portable, rapidly deployable runway surfaces that function on unprepared terrain. The legacy extends beyond military applications. Construction matting based on the World War II designs supports heavy equipment on soft ground at civilian sites. Temporary roadways for emergency access use similar principles. Even temporary event surfaces for outdoor festivals are derived from the military matting concepts. But the wartime impact remains the most significant. A technology that Axis planners couldn't replicate, that accelerated Allied victory by months or perhaps years. General Hugh Casey, Chief Engineer of U.S. Army Forces in the Pacific under General MacArthur, later wrote that victory in the Pacific rested as much on pierced steel planking as on any weapon system. Allied forces didn't just outfight the Japanese, they out-engineered them. They created airfields faster than the enemy could respond. They established air superiority not just through better aircraft, but through fundamentally better logistics. The matting was the bedrock of that superiority. The perforated steel panels that rolled off American production lines by the millions represented more than mere engineering innovation. They represented a fundamental difference in how America approached industrial warfare. Axis military planning focused obsessively on weapons. Better tanks, better aircraft, better artillery. American planning focused on systems, not just the weapons, but the infrastructure to deliver them where needed, when needed. Pierced steel planking wasn't glamorous. It didn't feature in dramatic battle reports, and few medals were awarded for laying it. But it enabled everything else. Every fighter that took off from a forward airfield, every bomber that reduced its mission distance, every casualty evacuated from a field hospital, all of it depended on steel panels laid by combat engineers working under fire. The Marines working at Henderson Field in August 1942 demonstrated something that would prove decisive. American engineers had imagined a different kind of war. Runways delivered on trucks, airfields operational in days, infrastructure that moved fluidly with the front lines. They turned that imagination into 2 million tons of perforated steel, into nearly 1,000 miles of runway, into air superiority across 2 oceans and 3 continents. The steel mats rusted eventually. The airfields were abandoned or paved over. The engineering battalions went home. But the principle endured. Victory in modern warfare belongs not just to whoever fields the best weapons, but to whoever can field those weapons where they're needed, when they're needed. Axis planners never imagined American engineers would unroll airstrips from trucks. That failure of imagination proved decisive. Sometimes wars are won not with weapons but with logistics, not through destruction but through construction, not by outfighting the enemy but by out-engineering them. 2 million tons of perforated steel proved that principle beyond a doubt.